Hello everyone. This is lecture 88 of Principles of Electric Circuits. In the previous sinusoidal steady-state analysis, the circuit's excitation discussed is sinusoidal wave with one frequency. In this condition, we can use a phasor to solve any branch variable. But sometimes the excitation is periodical signal instead of a sinusoidal one. We can use Fourier series to expand it into the sum of the sinusoidal signals with different frequencies. The circuits discussed are all linear circuits, so the sum of the responses produced by the sinusoidal signals with different frequencies is the response of any branch in the whole circuit. This is the main content of the following three lectures. In lecture 88, we will introduce Fourier series for periodical signals. It requires mathematical knowledge a lot. You will learn Fourier series in detail in calculus course and signals and systems course. We only apply some conclusions to circuit analysis without proving them. Periodical non-sinusoidal excitation is plenty in circuits, such as half-wave rectification based on diode. If US is a sinusoidal signal, the waveform of U2 should be like this. Obviously, it's a periodical non-sinusoidal signal. If U2 is the excitation of the next stage, what's the response? Besides, square wave and sawtooth wave are common waves in circuits. How to analyze their response? Fourier series is an effective tool for analyzing these signals. By any periodical signal satisfying Dirichlet condition can be expanded into Fourier series. We do not explain this condition here. The common signals in electrical engineering all satisfy this conclusion, so we can use Fourier series safely. Fourier series has many expressions. We use cosine and sine expression with every frequency here. When the frequency is zero, it's a direct current. The frequency of this component is omega, is called the fundamental wave. The frequency of these components is 2 omega, is called the second harmonic. The rest may be deduced by an analogy. These are the expressions of AK and BK. By combining cosine and sine components together, we can get the second expression. In other words, the component with some frequency is expressed by magnitude and initial angle. From the relationship between the two expressions, we can see once AK and BK are known, CK and theta k can be easily solved. The calculation of AK and BK is the content of the mathematics course and the signal course, and you are not required to remember their formula in the circuit course. Next, let's discuss the symmetrical property of the periodical signal. If a signal is an odd function, like this one or this one, according to the expression of the Fourier series, we can derive that this signal only has sine signal but no cosine. If a signal is an even function, like this one or this one, according to the expression of AK and BK, we can know it only has cosine component but no sine. A more interesting condition is the signal is half-wave odd symmetrical. What is half-wave odd symmetry? Let's look at this function. For this function, a period is from here to here. If we move the whole period signal half period to the right or left, it will be like this. This is just the part in the expression. If the signal before and after movement are symmetrical to the horizontal axis, the signal is called half-wave odd symmetrical. For half-wave odd symmetrical signal, from this expression, we can derive it only has odd harmonic waves. Here, I have a question for you. Why do we only discuss the half-wave odd symmetrical signal instead of half-wave even symmetrical one? You are encouraged to discuss this in the discussion group. At the end of this lecture, we will answer the question in lecture 53. This is a square wave generator. It has not only positive feedback but also negative feedback. In that lecture, we only told you this is a positive feedback circuit without explaining the reason. With the concept of the Fourier series, we can discuss why it's a positive feedback circuit. From the analysis in lecture 53, we know the period of the generated square wave is this. This is a square wave. According to the introduction above, this square wave should mainly have a sinusoidal wave with this period as a fundamental wave. The angular frequency of the fundamental wave is this. The capacitor represents a capacitive reactance under the fundamental wave. By substituting the value into the expression, the capacitive reactance is this. For the negative feedback of the sinusoidal signal, this is a voltage divider consisting of a capacitive reactance and a resistor. The divided voltage on the capacitor is this. From the aspect of the magnitude, 1/3 of the output feeds back to the inverting input by negative feedback, but in the positive feedback, 50% of the signal feeds back to the non-inverting input. The circuit has both negative feedback and a positive feedback, but the positive feedback signal is more. So overall, this is a positive feedback circuit. Well, this is the end of this lecture.